Well, welcome again. Uh, I was watching the previous video. Let me just get into it quickly. Without much waste of our time, today we want to do an introduction to remote sensing. In the past, we've just been dealing with the GIS, all right? And you know, our course combines GIS and remote sensing. So we want to introduce the remote sensing part. Okay, what do we expect? Of course, as usual, I'm going to introduce the session. I'm also going to talk about the electromagnetic theories, just a little bit from the past up to present consensus. Then we'll talk about present consensus. Then we're going to talk about the electromagnetic spectrum. And then we'll have a brief look at the interactions of light, just this light with the atmosphere. Then we'll look at interactions of light with target objects. And then I think we will also talk about the process now of remote sensing. And then there must be a conclusion. There must be also a class exercise. Okay. I wish to remind the class that we defined during the definitions of terms the issue of remote sensing, okay, as our introduction. Now, when it comes to the theories of electromagnetic radiation, I wish to speak here the fact that electromagnetic radiation is just light. In light, but in scientific terms, we call it electromagnetic radiation. And there were, in the past, there were arguments about what is the nature of this electromagnetic radiation. And the scientists who started working on it. This one says that, the other one says that, and so we have the particle and the spectrum theory proposed by Isaac Newton. We have also the theory of heat by Clausius. And then there is a magnetic and electric fields by James Clerk Maxwell. And so we also have Wien's law of radiation. And then there came a time when there was quantization of black body radiation by Max Planck. And then Einstein now put the entire issue almost to rest by proposing the photoelectric theory of light. Okay, so Newton said that light is composed of small, tiny, many particles that are moving at high speed and bouncing back. And that one was called the capsular theory of light. And Rudolf Clausius, this man worked on heat, the theory of heat. He's the one who suggested that heat actually is a form of energy. But then previously people were saying, heat is made of a fluid like water, okay? This man, German scientist, Clausius. Then we have James Maxwell Clerk, who worked on, who suggested that light is composed of fields of electric nature and magnetic nature alternating like that. So basically what this man said is that light is a wave. Are we together? Okay. Then the other interesting individual is Wilhelm Wien. He lived those times, and this man produced a law of black body radiation, which we refer to Wien's law. You can Google and search, you find this law in details. Okay. Then there came Max Planck, okay, who suggested that light is formed of particles of energy, and that became founded the theory of quantum mechanics. And finally, Einstein came in and proposed the photoelectric theory, where today we are saying that light is composed of the photons. So now what is today's consensus? Today we are saying that heat is an energy, just as it was proposed by Clausius. Today we are also saying that light exists as a wave, both as a wave and particles, which we are calling the wave-particle duality, okay? Just as proposed by Einstein. Then we are also saying that light is composed of alternating electric fields as well as magnetic fields, just as suggested by James Clerk Maxwell, okay? And because it is a wave, we use that wave equation there, where we are saying the velocity of light is equal to the wavelength multiplied by frequency, okay? So V there is velocity, lambda is wavelength, and F is frequency. For those who will remember the basic physics, this is what we imply, okay? And when you look at light, you split it, the light that we see, you find that there are those components within, and that forms what is called the spectrum, okay? So that leads us to, we want to describe the electromagnetic spectrum. And we are saying that this is composed of short wavelength light up to longer wavelength light. And most of this spectrum, we human beings are unable to detect. We cannot see with our naked eye. For example, we cannot detect the microwaves. We cannot detect gamma. We cannot detect X-rays. Okay, so the electromagnetic spectrum is bigger than the human eye can detect. Okay, and several regions in that spectrum are important to remote sensing. For example, the UV, part of the short part there, is very important in remote sensing. Light itumona nayo it's important, okay? It's important, but to a limited extent. So if you split that spectrum now into those components, you find that those are the wavelength values for each of those components. For example, violet, 0.4 to 0.446. I think this is micrometer. And then blue and things like that. So within that spectrum, there are those components. There is green, there is yellow, there is red, there is infrared. You can go on and measuring those values. Okay. And then radiation in the reflected IR infrared region is used for remote sensing, and this is especially in thermal imaging. Okay, so most of these are useful in remote sensing. Okay, and then the portion of the spectrum of more recent importance is the microwave region, which is important in microwave remote sensing. Okay. What else? Furthermore, we want to look at the interactions of light with the atmosphere. And there are various forms of interactions, and because the atmosphere is formed of particles of gases and many other components, okay? And so they affect the radiation in as it is traveling through the atmosphere, okay? So we are saying that as light is traveling in the atmosphere, it may be scattered or absorbed accordingly, okay? And so where does the scattering happens? Scattering happens when particles or large gas molecules are present in the atmosphere, interact with and cause the to be redirected. So scattering is just basically light kauma more than yachinja direction. Okay, they change the path, and these scatterings are in three types. The first one is what these guys are referring to as Rayleigh scattering, and this occurs when particles are very small compared to the wavelength. Okay, and particles such as the dust, small specks of dust, nitrogen, and the oxygen molecules are involved here. Then there's the Mie scattering, which happens when the particles are just about the same size of the wavelength of radiation. Then there is non-selective, which happens when the particles are much larger than the wavelength of radiation. Okay, we move forward and look at absorption. What happens? Okay, and we are saying that this is another mechanism or interaction of light with the atmosphere where molecules absorb radiation, okay? Like for example, the ozone, carbon dioxide, and water vapor. These are the three main absorbents of these radiations, and you understand why there is this issue of global warming and climate change is because of these particles. So ozone serves to absorb UV, okay, which is ultraviolet radiation. Then carbon and the other greenhouse gases, absorb the infrared or the heat part of the spectrum. Then, I think those were just two. And those areas of the spectrum which are not severely influenced by atmospheric absorption and are useful, those are useful to remote sensing, are called atmospheric windows. They are not influenced by the atmosphere. They cannot be absorbed. They are rarely scattered. So they provide useful portions to remote sensing, and they are here referred to as atmospheric what? Atmospheric windows, okay? And the visible portion of light is one such example of an atmospheric what? Window. Okay, then the next issue is that of interactions with target objects, okay? We are talking about radiation that enter the atmosphere and reaches the what? The surface. And according to my research, there are three forms of interactions that take place, okay, upon that energy entering the atmosphere. So there could be an absorption, A, or it could be transmitted, so it passes through, or the light may be reflected, okay, or refracted, okay. So refraction occurs when radiation bounces back off the target and is redirected, okay. And in remote sensing, we are interested in this reflected, light, okay. And reflection, when the surface is smooth, we get a specular or mirror-like reflection, where almost all the energy is redirected. And you also may encounter diffuse reflection, okay, or diffuse reflection, where the light goes in different, directions, but scattered, okay, which is really less useful in remote sensing. And if you talk about interactions with leaves, the chlorophyll that is in the leaves of plants will absorb the red and the blue wavelengths, but it will reflect the green wavelengths, which is why, of course, plants look green, isn't it? And then what about water? We are saying that the longer wavelength visible and near infrared radiation are absorbed more by water than shorter wavelengths. And this is one reason, as we are moving forward on satellite images, we find that where there is a water body, it's dark because it absorbs that part of the spectrum. So by measuring the energy that is reflected or emitted by targets on the Earth's surface over a variety of different lengths, we can build up a spectral response for that object. So different objects have different reflectances. They interact differently with light. And so because of that, we can have a spectral signature. They call it a spectral signature, okay? Moving forward, we wish to look at the process of remote sensing. And for the sake of uniformity, we wish to repeat this definition here, where we're saying this is the science and to some extent art of acquiring information about an object without actually being in contact with that object, okay? And this is done by sensing and recording reflected or emitted energy, which is radiation, isn't it? Okay, and this may involve processing, analyzing, and applying that information. So if you can see from this diagram here, which I extracted from this famous Canadian book on remote sensing, there must be a source of energy here at A, okay, like the sun, or maybe even the sensor itself may produce that. Then that energy travels, which this energy is the same as the light, the light we are talking about. It travels through the atmosphere at B, then it hits the target at C. Then it is reflected, it is absorbed by a sensor at D. Part of it will be reflected back to the target. But this sensor now is going to change that energy into electronic what? Electronic information. Send it over to a sensor on the surface of the Earth, or even transmit it to another sensor. And then at this point, the data will be manipulated, worked on, and interpreted. Then it can also be applied. I think that is a short explanation of the process of remote sensing. And so there must be a source, as I said, which is the source of energy, and that is A. Then second, radiation have to interact with the atmosphere, okay? Then third, it has to also now enter the atmosphere and interact with the target. Then the energy at D is recorded, okay, captured, okay. Then there must be a transmission reception which is occurring at E. Then there is interpretation and analysis at F. Then that interpretation and analysis must be applied, okay. So these 7 things here comprise of what we are calling the process of remote sensing. Thank you. Now, in conclusion, we are saying that today's consensus on the nature of light is that it's a wave-particle duality. Then the phenomenon of remote sensing should therefore be simple here. And wonderful. Simple and wonderful, right? Then our class exercise is that we have to explain the weaknesses of the theories of light as explained by Newton, Maxwell, Wien, Marx, and Einstein. Okay. Thanks for your attention. May the good Lord bless you all. Questions, please. Now, the other time, I just had a pinch. So, now, and then don't push. Instance of.
Yes, Mr. Malunga. I was just clapping for you. It was a nice lecture.
Thanks very much. Thank you. Now, butuka feva kalamba. Kairi mina chiposa sana nishta.
Nimbona. It's fine. Now cruiser, but we are.
Where is Gertrude? Gertrude, I can't see you here. Where are you? Okay. Oh, I need to. Where is Gertrude? I can't see her here.
Sir.
Yes, please. I have a question.
I just wanted you. No, just wanted to show me the exercise, the class exercise.
The class exercise.
Yes.
Okay, no worries. Yeah, this is the one here.
Okay, sir, thank you.
Have you copied?
Yes, sir.
Thanks very much. Thank you. Where are you? I want to mute you. Hiding. Participant number 2. Mr. Svandesa.
Yes, sir. I just wanted to, at least to pat you on the back. The 2 sessions that I've attended so far, they have been tremendous. Go ahead, please. I'm enjoying. Thank you very much.
Thank you, sir. Thank you. The other time you joined, I couldn't greet you because you joined in the middle somewhere. Otherwise, I very much wanted to greet you.
Okay, now you can go ahead, sir.
Thank you very much, sir. Thank you. Okay, are we fine thus far? Okay, then thanks very much. Okay. Eliza?
Yes, sir. Good morning.
How are you? How are you?
I'm fine. How are you?
I'm fine, thank you.
I've got a question for Mr. Silandi.
Okay.
Can I go ahead?
Yes, please. Though I've been warned that the time is almost up. You can go ahead.
I just wanted to ask him if we'll be having other sessions in other courses, or will it be only GIS and wildlife?
Oh, yeah.
What will happen to the other courses?
Yeah, sorry, which is why, for me, I wanted us to move faster in these 2 courses so that we can leave some room for others. You understand?
Yes, sir.
Yes, so don't get tired. Let me just put Mr. Swan on to speak.
Me on?
Yes, sir, you are on.
Okay, please. Just like you have alluded to, we have got a timetable that will come out. And then as far as we are concerned, most of the lecturers were done with the first term's work. So what is coming out would be probably for the second term. So this time around, we are just working on the timetable for ODL, open distance learning. And then these guys, when their time comes, we will communicate to them and then lessons will start.
You've heard, right? You've heard, Eliza?
Yes, sir.
Eliza?
Thank
Okay.
you.
Okay, you're welcome. Thanks.
Thank you very much.
Mr. Nsofu?
Yes, it's just a comment also on the same. I
Yes,
think
please.
like what Mr. Swanda said, we have worked on modalities for each staff to know how to use the app. And so everyone now is aware and they know how to use the app. So most likely, very soon, you will see the timetable like Mr. Swanda has alluded to. We are going to have almost all the members of staff teaching. If some fail to do the Zoom, we are going to do the voice narration on PowerPoint presentations, which will be sent to the groups or to individual students, so that at least everyone is able to get what we are teaching.
Sure, sir. Participant number 2. Where's participant number 2? Okay. All right, then we can now leave the session before time, at least this time.